Good morning, mathematicians. Welcome back to a new episode. And by a new episode, I mean an old episode. And by an old episode, I just mean we're continuing where we left off last time. And now I'm gonna trust you guys that you all did your homework, of course, and so that I can give you guys the answers and trust that you already worked on it on your own. Good morning, Edit Smith. For the record, I should officially vindicate Edit Smith. I don't know how many people are tuned in yet, or how many people remember when Edit Smith said something. They said on Reddit they got banned or their comment got deleted just for being conservative, and I was like, no, there's no shot. There's got to be more to the story. But then they sent me the screenshot, and there is, I mean, slightly more of the story, but not really. Basically, someone said F Republicans, and they said F Democrats, and then the Republicans comment stayed up, and the Democrats one got removed. And I just feel like no matter which way you lean, that is a double standard, and that's stupid. So, official on the record vindication of Edit Smith. Let the record show. Okay, let's finish with this computation. So, what did we have here? Right. So let's compute the zeroth cohomology. Right. So this is the this term here is hom of p naught z, and so we take the cohomology of this part of the sequence, and that will give us x0. So we're going to look at the kernel, right, as I wrote down here, the kernel of precomposition with multiplication by n, that should say, modulo the image of the 0 mod n map. Well, let's think about the kernel of this map. So suppose f is in the kernel of this map. Well, what does that mean? That means that f, so that means that f is equal to, let's say, for all m, the integers, fm 0 is equal to fm is equal to g n times m. The integers are commutative, so of course we can put this on any end. So for some g in where, well, that g, if we go back up in the sequence, that should be a hom from z mod n into z. For some g from z mod n into z. Then we can factor out both. We can factor out n times m, let's say, because it's a z module homomorphism. And then n is definitely non-zero. We could choose m to be 1, right? Because this has to hold for all m. So this just becomes 1. We can divide through by n. And what do we find? Well, that g1 has to be equal to 0. I.e., for an arbitrary m, that means that gm, that means that, what does that mean? That means that fm, which is equal to gnm, which is equal to n m times 0 is equal to 0, right? So in other words, f is the 0 map. So the kernel itself is trivial. And so certainly the quotient is going to be trivial. So what have we determined? We've determined that x0 of z mod n into z is trivial. Trivial cohomology. Okay. What about x1? So now we want to compute x1. We know all the higher x are going to be trivial, but this is going to be going back up. This will be the cohomology at this term, right? So, because this is like hom of p1 into z. And this is the 0 map here, right? So certainly in this case, so it's going to be the kernel of the 0 map modulo the image of, what was it, precomposition by multiplication by m. And hello Zongshu, hello Arad. Yes, you're right. Hom z mod n z into z is just 0, exactly. And so here, well, the kernel in this case is everything. So the kernel is hom z. And now let's work out what the image is. Well, also note that hom z, right, this is isomorphic as a module to just z. This is a general ring theory result. But to see this more explicitly, maybe how the bijection goes, how the module homomorphism goes, is it basically sends a m to a map fm, where we define fm to be the map that sends 1 to m, and that completely determines a module homomorphism. So so with that in mind, let's think about what's in the image. Hom z is isomorphic to z as a ring even. Yes, that's true. That is very true. So how do we, what was I going to say? We want to determine the image of the multiplication by m map, right? So if we just have some arbitrary f, whatever f happens to be, in hom z, well, let's look at what happens when if we apply, f composed with the multiplication by m map. Well, and maybe I should even, sorry, let me write it this way. So I'll call this f sub n, and I'll compose this with the multiplication by n map. And if you look, if we multiply at 1, this is f sub m at n. So it's a module homomorphism. We can pull out the n, This is n times f sub m at 1, so that's equal to n times m. So in other words, we can see that basically every map f sub m in the domain is going to get sent to a map which is some multiple of n, right? So in other words, the image of this map, and again, you can choose any n to get such a multiple. So the image is basically f sub n m as m ranges over all the integers. So we've got the sequence where z is multiplied by n, and then it appears that one of the cohomology is, and the rest vanishes, but you don't know which cohomology that is. Okay, well, we can talk about that in a second, but let's finish computing the cohomology here. Let's finish computing it in this example. Oh, it is. Oh, I see what you're saying. Yes, it is. It is basically this example. Yeah. So, right. Yeah, this term here is 0, and this is our z, and this is our z, and this is the multiplication by m map. And well, we already checked the cohomology here is trivial, right? We already checked the cohomology at this term is 0. So the non-trivial cohomology is here, which we're about to finish verifying. Right, so finally so we have our image here, right? This is fn m, such that m ranges over all the integers, and well, I suppose we should be a little more technically precise here, but hopefully it's not hard to see that surely this is z modulo, nz. Right? I mean, to be totally precise, to be really rigorous, I would just I would look at take this map, compose it with the projection down to here, and then use the first isomorphism theorem to see that the kernel is the ideal generated by n. That's how I do it more rigorously. Yeah. So what's the conclusion of this? If we track back through a bunch of our steps, remember we started off with ZR. We wanted, we were thinking about a finite abelian group, and we wanted to know what its ext was into z. And so if we combine all of our computations together now, so arbitrary finitely generated abelian group, its ext into z is given by the following. So it's just always the case that that ext is given by Hom. Ext0 is always given by Hom. So it'll be this when n is equal to 0, and when n is equal to 1 for x1, we actually just recover the torsion part. And it will be 0 for all higher x's. And in fact, this should just work out to z to the r. This should just work out to z to the r. Yes, right, because this is just r copies of z. Yeah. So, in other words, for a finitely generated abelian group, x0 of g recovers the free part, and x1 of g recovers the torsion part. By the way, in general, right, because free implies projective, in general, you can consider this map, this example immediately generalizes, even in the non-commutative case. So now it is important that we think about this as being multiplication on the right. And well, actually, and then mind you, I guess I have to be careful about left, right, and ideals and stuff as well. But you can use this. This is going to be a free resolution. This is going to be a free resolution. If R is an integral domain anyways, because otherwise this map is not injective. So if R is an integral domain, then you can use this. You can use this to compute this or x of this. So this is a good. Here's another exercise I'm challenging you with, is do this computation. Yeah. How am I with differential geometry? Trying to compare the Laplace Beltrami and Laplace de Ram operators, specifically on one forms. Interesting. I don't know if I'm good enough to help you, but let's look it up. Apparently there's a Weizenbach identity for that, but you don't really get how it's formulated. Interesting. His MacBook M1 good? I don't know. I've never used an Apple product, especially for students who are pursuing math. It's funny that you asked this, because I was just looking. Someone made a post on the UCalgary Reddit today. They were like, here's the laptop I recommend, and it was just like one of the like child's play laptops or something. And I think they just made it as a funny response, because everyone's been making posts about what kind of laptop they need. I don't think the laptop you get really matters at all for math, or probably for most things. Yeah. Like, does it have the internet? And is it like, I mean, okay, if it's like 10 years old and painfully slow, that might be annoying. But otherwise, yeah, I really don't think it matters at all. The only thing I would say personally for me is I've had a lot of laptops break at the hinges. And so someone recommended me a ThinkPad. So that's what I'm running now. And it seems to be, yeah, seems to be good and sturdy. So, yeah, but there are pen and paper recommendation threads on Math Overflow if you want to be that guy. Yeah. 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 But yeah. Honestly, I don't think. Yeah, if you like Mac, then get a Mac. If you don't, then don't. I certainly wouldn't worry about any particular model, M1 versus K15 or whatever. I don't know anything about Mac. Yeah. Okay, so we did X. Okay, let's talk. Let's look at this. Let's look in this Laplace-Beltrami stuff. Laplace-Beltrami versus Laplace de Ram. On functions, the Laplace de Ram operator is actually the negative of the Laplace-Beltrami operator. Interesting. Interesting. Ooh, Laplacian and Hodge Laplacian. Maybe we should look at that. I should say that I'm yeah, I need to look more into the Laplacian. There's a line of thought I had about stuff to do with the Laplacian. I mean, apparently there's some. Okay, let me not get sidetracked. Let's look at this. Right. Right, this is Laplace de Ram. Right, Laplace de Ram is defined by this. Right. When computing Laplace de Ram operator on a scalar function, we have this, so that this. Up to an overall sign, the Laplace de Ram operator is equivalent to the previous definition of Laplace-Beltrami when acting on a scalar function. Interesting. The sign is merely convention. Both are common in literature. Laplace de Ram differs more significantly from the tensor Laplacian restricted to act on skew-symmetric tensors. Weizenbach. I actually don't know what a Weizenbach identity is, so we're gonna new tab that. So fun fact, especially Rod, because you seemed interested in graph theory before. You can actually realize the Laplacian matrix of a graph. Basically, if you, what is it? I think. So the Laplacian matrix of a graph, if you view. If you think about operators, so you think about functions from the vertices of your graph, and you think about the space of functions from edges to your graph, then you can write down like a discrete differential. So I think the differential goes this way. So it's something like, so I don't remember if you need to take a directed graph, or maybe that's for the signed Laplacian, but it's something like, so your differential of f defined on, or no, maybe the differential goes the other way. Maybe it goes the other way. So it's like the value of the differential at an edge will be, so I think there's different versions. I think you can take it to be the sum of the values on the two vertices, or if you have an orientation I think if you do it with respect to an orientation, then you like take a difference. And then you can also similarly define a co-differential. We could do the tour today. We could start talking about tour today. A co-differential. And then the Laplacian matrix is, if you look at the basis of the indicator functions on each of the vertices, then the Laplacian is exactly the de Rham Laplacian. Starting to look like a special case of the chain complex associated to a simplicial set. Oh, that is the most highbrow way to say it. I mean, it kind of is, right? You can definitely, yes, you can definitely do that, and then in fact, you compute. You can compute the first cohomology of your graph, which is also known as cycle space. It's basically corresponds to circuits in your graph. There's a whole interesting thing for us to discuss there, but anyways, I just wanted to mention. Not so highbrow for use to simplicial sets, I guess. But I mean, I don't know. Simplicial set, I don't know. I mean, I would have said, oh, that, it looks like some sort of, cohomology thing or a simplicial complex. I don't know. Simplicial set is maybe, but you're right. Yeah. I don't know. Are we good on the Laplace Beltran? I don't think I answered your question, but it seems like, but you said Laplace. But maybe you answered your own question. Laplace de Rham is the same as Hodge Laplace. Yeah. But I don't know how much further help I could even possibly be. Oh, I do want to look at what the Weizenbach. Wait, what is this that I opened up here? Oh, Laplacian and Hodge Laplacian. You're just saying Hodge Laplace is another name for the same thing since it came up in search results. Right, okay. Weizenbach. Mathematics, differential geometry, elliptic operators on a manifold with the same principal symbol. G invariant between vector bundles associated to some principal G bundle. Interesting. There are two notions of Laplacian on differential forms: over-oriented compact Riemannian manifold. The first uses the divergence operator, defined as the adjoint. Right. So that's the Laplacian. Oh, this is interesting. Yeah. The Levi-Civita connection. Okay, wait. How is that defined? The Levi-Civita connection is a unique affine connection on the tangent bundle that preserves the Riemannian metric and is torsion-free. Interesting. This is very interesting. Because in part of what I find interesting about this is sorry Zongshu, there's a chance we may not get to tour today. I'm distracted now by differential geometry, but if we don't talk about it today, we'll talk about it tomorrow. But from my master's research, there was one of the ingredients is there's a certain connection that we took. Actually, technically, it was a super connection, which just means that there was some it respected some Z2 grading. Whoa, what's that hyper E that I just drew? So there's some Z2 grading that also has to be accounted for. And then one of the things that we needed to construct from this particular connection was basically you look at, well, again, there's changes that we make to the usual setup because, again, there's a Z2 grading. Good morning, Yamin. There's a Z2 grading that we need to take, but we basically take this form, which is the trace of the exponential. It was basically like the churn form. But there's some like extra fancy things. Well, there's two forms. There's phi and then there's psi. And then the psi has, we precompose with some sort of operator. Good morning, Lola. So, good morning, nerdy Quagsire. Everyone's waking up. Yeah. But this is also all happening on. Basically on a symmetric space. So basically there's it's a Lie group modulo it's maximal compact, and there's some results that I was able to prove about these things, but I could only take them so far. They sort of depended on getting some numerics in small cases and then inducting from there. I didn't get a fully general proof that I wanted, and I always kind of wondered about how to go back, and I thought that maybe one thing to do would be somehow go back, because there's something about there's some sort of like Laplacian right on the manifold, and it should this is related to the Casimir element. And I know that there's some way to get like a connection out of this. And I thought that maybe the sort of general theory going on here, I could maybe somehow relate to this. These are all very vague thoughts, but anyways. You study a bit of Hodge theory, but you never understood why harmonic forms and the Hodge Laplacian depend on the choice of Hermitian metric. I mean, isn't I think part of it, you need to have a metric to have canonical identifications between vector spaces to their duals. Yeah, because I think, like we were talking about before, like we have our differential and our co-differential, right? And those are basically defined, like, you can take like your exterior derivative, and then the co-differential is basically defined to be an adjoint linear operator with respect to some pairing, right? And so it's like inherent. It's inherent in this inner product. Right. Yeah. You're actually doing all this stuff with symmetric spaces in mind. Oh, interesting. A Rod Kristaps collab in the future. Maybe a stupid question, but what is the key idea behind showing that the connection exists in this case as a super connection? Well, it's not that it's the key idea isn't showing that the connection exists. It's just there's there's a few more ingredients that go into play here. So I should say in this case, G is actually UPQ, and K is UP cross UQ, And this form, we basically take the degree 2q part of this form. And it turns out that this agrees. It turns out that phi is something called phi of 2q is something called the Kudla-Milson form. And I don't really understand the general theory of this, but vaguely it has something to do with like the wave representation. And I don't know. Good job, Ken. Woke up slightly earlier. Caught some of office hours. I don't really know a ton about Hodge theory, to be honest, Yaman. So I don't know what to recommend for learning it quickly. Yeah. Why do you need to learn it quickly? Got a Hodge theory course coming up, or you need it for research, or what's the deal? Anyway, so there's something going on here, and the point is my master's supervisor. So this has some other definition by other means, and then my master's supervisor and his collaborator basically said, well, there's this particular kind of super connection that you can cook up. And then they showed that it recovers the Kudla-Milson form. And they also build some kind of other particular form out of it. And then the point is that these forms, phi and psi, should somehow generate representations of G, somehow passing through the wave representation. Again, I'm murky on these details. Like I proved some basic things, like using like the theory of weights, they generate like a highest weight representation, something like this. And then the point is when you know that they are highest weight representations of a particular weight, somehow this then gets fed into the theory of Eisenstein series. Again, I don't really understand, but somehow this gets fed into the theory of Eisenstein series, and knowing that these have some particular weight gives you information there. You're studying Borel's computation of ranks of K-theory of rings of integers. So that'd be an apt collab. So actually, this does have something to do. There's something else. Symmetric spaces used to compute cohomology of arithmetic groups. Yeah, I don't know as much about that, but there's something else going on here, which again, I never really fully understood. There's something going on with Arakelov geometry. Because somehow, so part of why these forms matter, so there's like one part where they're connected to representation theory, but then there's another part where you basically, these forms somehow should also correspond to certain cycles in G, which then also compare to, there's like this arithmetic Chow group, and so your arithmetic Chow group should somehow, like, what is it? I think if you have like a number field, like the corresponding arithmetic Chow group, you should basically have yeah. See, I don't remember all these details are too murky now, but there's something like the way that the arithmetic Chow group is built. If you have some like sufficiently nice space over here, then you have like your original Chow group just viewing this as an actual scheme, but then somehow you get like there's like associated like complex points of this that have a manifold structure. And then the idea of like the arithmetic Chow group is that somehow you bump it up so that this data is like somehow parts of the original Chow group, but then there's some extra data coming here. These all turn out to be Hermitian manifolds. Oh yeah, and this is why I got started on this whole tangent to begin with. Part of what Arad was saying when we were looking at the this this is why I started talking about this. So this uniqueness, right? The fact that in the Riemannian case we have this unique connection. The Levi-Civita connection is a unique one, satisfying this well. In this case, there's also if you have a choice, if you have a Hermitian metric on these like holomorphic vector bundles, then you also have a special choice of connection that respects the Hermitian metric, and that goes into the definition of the super connection. So basically, the super connection is really, you have this Hermitian. Maybe I shouldn't put the H down there, but you have this Hermitian part, and then there's just this other operator that you tack on that deals with the grading. And that's basically how this connection ends up getting defined. So yeah, I don't know where I was going with all of that, but stuff's cool. Yeah. Yeah. You don't want to spend a lot of time reading a textbook on it. I mean, yeah, but this is math. If you don't want to spend a lot of time reading a textbook on a subject, then you're probably not going to get super far in that subject. I mean, it's not necessary. I mean, some subjects are more, I don't know, you can pick up little scraps and bits from disjoint papers and PDFs, but and some you do just have to sit down and go through a tome. But I don't know, it's just kind of how it is. I do need to get myself a nice cool Millie. I do. Yeah. This flavor of differential geometry is so algebraic, is it? Have I really said anything too algebraic so far? Maybe. I don't know. That's the best flavor. Exactly, Rod. Yes, that is my favorite Sun Tzu quote. The only good thing about differential geometry is the algebraic parts. Well, I mean, I'm biased towards the algebra, but I would not agree with that, actually. My heart is more open to analytic things than it has been before. Okay, I think that'll probably do it for office hours for today. I think I want to go get to work on some stuff. But yeah, we'll probably Zongshu. I don't know if you hear, but we'll probably talk about some Tor stuff tomorrow. Do some computations with Tor, but it's I mean, now that you've seen Ext in detail, you're probably more prepared to go read about Tor. It's a very, very similar sort of thing. You too, Arad. Have a productive day, everyone. Go prove some things about Tor.